Hello everyone, welcome back to a Geostats lecture video. And in this lecture video, I want to go through the R implementation of the Getis Ord G. Now, Getis Ord is typically what you would see behind things like hotspot analyses. And so understanding how to implement this in R is extremely important. So what we're going to do is we're going to follow much the same sort of general steps that we followed with local Moran's eye. With a couple of small differences. The key difference being that for whatever reason, the function that we use for Getis Ord does not produce a p-value. So we actually have to go through and manually calculate the p-value and then adjust it again for that multiple hypothesis issue. So the way that we're going to approach this is with the local G function. But before we do that, I want to just reiterate what I've done already. I've copied and pasted the 3 lines of code from the previous video. So if you don't already have these in front of you, just take a second, pause the video, and recopy them. Just to sort of recap what we're doing, we're loading in the data. Again, this is the Georgia data set from the GIS tools package. We are also creating a neighborhood connectivity with the rooks case, again, because queen equals false means we're using the rooks case. And then we're converting that neighborhood matrix to a spatial weights matrix. Okay, so that's all we've done. This is, again, this should hopefully be a complete review for everyone. So what we're going to do now is we're going to implement the local G. So we're going to use a function literally called local G. And again, this is coming out of the spdep package. So spdep : local G. Okay, so G and G star local spatial statistic. Okay. So again, we're calculating the G statistic, which is just a Z value, and this Z value is going to be extremely important. So what we have here is we have the function local G, and you'll see that it takes in the 2 parameters that we pretty much see all the time, X and list W. X being the data set that we're in, or the variable from the data set that we are interested in modeling, and list W being our spatial weights matrix. Now, again, I just want to point out here the key difference between this workflow and the workflow for local Moran's eye is that if you look through here, there is nothing about a p-value, which means we have to go the next step and actually calculate those p-values and adjust them ourselves. But we'll cross that bridge in just a second. So let's go ahead and code up our local G statistic. Okay. So again, we're calculating local G, so I'm going to call that loc G. And we're going to be setting that equal to the spdep packages local G, which takes in as parameters the X and the list W, which again, X is our data as our variable of interest. So we're going to call in the Georgia data set. Oops, I actually have to run these lines of codes first because I actually don't have anything loaded. There we go. Now it's going to recognize the Georgia data set. So if we do Georgia at data, $, so we're accessing the individual variables, and we want %rural. Okay. And then our list W, this is again our spatial weights matrix, so we would do the SWM here. Okay. So if we run this, we hopefully don't get any errors. Perfect. So let's go ahead and examine the output. Okay. So what you'll notice is that unlike the local Moran's eye, we only have one value here. This is a vector. This is not a data frame. Right, we only have one value. This value is the G statistic. So we have no sort of reference for whether or not they're significant or not. We just have the G statistic. Okay. So hopefully that makes sense. We then have to sort of put some statistical significance on it by calculating the p-value. Okay. So the way we're going to approach calculating the p-value is through this function called Pnorm. This is from base R, and you'll see that Pnorm takes in a parameter of Q, which is a vector of quantiles, and then the mean and standard deviation, we don't want to mess with these. And then we want to mess with this lower dot tail. And we want to set lower dot tail to be false when we run this. And the reason is because if we keep it as default, right, it's assuming that we're looking for values less than or equal to x, which is not what we want. We actually want the values greater than x. Okay? And so what we want to do here, and this is because we're dealing with z, right, again, the g value, the g statistic, is actually just a z-score. It's a z-score of the statistic, or the statistic is a z-score. So we already know that it has a mean of 0 and a standard deviation of 1, and that it's coming from a normally distributed distribution, right? That's what a z-score is. So what we can do here is we can say that the p-vals are equal to, and this is the part where hopefully you follow along. We're going to call the p-norm, and we're going to set q, and we're going to set lower dot tail. We're going to set lower dot tail equal to false. Now this q here, this is going to be a little bit different. So what we're going to be doing is we're going to be doing 2 times the absolute value of local g. So the reason that we're doing absolute value is because we want to account for both the positives and the negatives, right? Because in this case, right, extreme negatives and extreme positives are both things we want to test for. So we're going to set this to be the absolute value so that we're testing for both of them. Okay, so hopefully this makes sense. We're basically setting this up so that we pass in quantiles based on the absolute value of the g statistic. Okay, so if we run that, and then we examine our p-values. Okay, so this right here, these are our uncorrected p-values. So this is what it would be if we have if we just assumed that there were no issues with multiple hypothesis testing. Okay. So let's go ahead then and adjust the p-values. So the way we adjust the p-values is with a function called, it's from the spdep package, and it's a function called p.adjustsp. Okay, forgot my question mark. Right, so this adjusts the local association of the p-value, and it does it it incorporates this idea of neighborhood connectivity. So this is addressing both the issue of multiple comparisons, but also the issue of spatial association. So what does it take into account? It takes into account the p-value, which we just calculated. It takes into account the neighborhood matrix, neighborhood connectivity, which is our NB object that we calculated in the beginning, and that takes in a method. And this method is basically just how do we want to adjust them. And what we want to typically what you want to do is you want to do Bonferroni, because Bonferroni is going to be the most conservative. You could also use FDR. Actually, no, let's go ahead and use FDR. Actually, no, let's do both. Let's do both. Let's do the adjust the p-value of Bonferroni by calling, so we'll call p-vals underscore bon, and this is going to be equal to spdep p dot adjust sp. Again, it takes in the p, the neighborhood connectivity, and the method. So our method is going to be Bonferroni for the Bonferroni correction method. Our p-value is going to be equal to the p-vals that we just created. And then our neighborhood connectivity metrics is going to be the NB object that we created in the first place. So if we run that, okay. I'm going to hold off on actually examining these because I want to look at them after the fact, after we've done all of them. So let's do the false discovery rate, or FDR. So pvals underscore FDR. Again, we're going to call in the spdep p dot adjust sp. Same parameters, p, nb, and method. But in this case, we want method to be FDR for false discovery rate. Our p is still going to be our p-vals because we're going back to our original p-value. And we want our neighborhood connectivity to be NB. Okay, let's go ahead and run that. So we now have three different p-vals. We have our original uncorrected p-value, which makes no attempt to care about multiple comparisons. We use Bonferroni, which is usually the most conservative, which means it is the most likely to throw out significant results in an effect to correct for when we might get false positives. So let's go ahead and do the false discovery rate, which we already did. So let's go ahead and compare them. And the way that I want to compare them is I want to do this. So what I want to do to just see how many significant results we keep, I want to compare the length. So let's quickly just compare the results. So if we compare the Bonferroni to the false discovery, let's do compare. So we'll do p-val equals the length of, and we want p-vals at p-vals greater than or equal to 0.05, right, our standard alpha. Okay. So let's do Bon equal to the length, and we're going to do the same thing. The length of pvals underscore Bon, index at pvals underscore Bon, greater than or equal to 0.05. Okay. Oh, I'm so sorry. We actually want less than. My apologies. We want less than or equal to, not greater than. Right, because less than. Okay. So, what about FDR for false discovery rate? Length pvals underscore FDR, indexed at pvals underscore FDR, less than or equal to 0.05. Okay, so let's just quickly pval Bon and FDR. Okay, so in this particular instance, Bonferroni and false discovery rate gave the same results. Let me just make sure I didn't make a mistake. It does not look like I did. But you can see that they've both drastically reduced the number of significant observations. Right, before the correction, we had 75 significant G statistics. After addressing that, we dropped down to 47. So you can see how important it is to address those p-value issues. So finally, what I want to do is I want to just plot the significant results, and we're going to use the FDR. So what I would need to do first is attach the data, attach the G and P values to the data frame. Right, so we're gonna call this GEORGIA underscore sig. This is gonna be equal to Georgia. Actually, we need to attach them first. GEORGIA at data $. We'll call this lock G. It's going to be equal to data.frame lock G. And because there's only one column in the lock G, we can do this and we won't have an error. Maybe we will have an error. What happens if we don't do that? There we go. Okay. So then we'll do the p-values. Georgia at data $PVal. And I want to pass in the Bonferroni corrected p-vals. So we will do equals p-vals underscore bon. Okay. So now we have the data attached. So I want to go ahead and create a significant GEORGIA underscore sig. And we're going to set that equal to GEORGIA indexed. We want to keep all of the columns, but we only want the observations where our GEORGIA at data $, where our p-val is less than or equal to 0.05. Okay. So if we run that, we now have our significant values, and we're going to go ahead and quickly just plot them by creating a T-map. This is going to look exactly like what we did at the end of the Moran's eye video, where we're passing in the first data set as our boundaries. And then we're passing in the second data set as our to be colored based on, in this case, we want lock underscore G. I'll put that in quotes. So if we run that, and then we call it T-map to look at the output. So these are our statistically significant G statistics. And so you can see areas of strong negative. So these would be the areas where you have a clustering of negative values or low values. And then you have here, this would be where we have clustering of high values. So low values, high values. Hopefully that makes sense. I know this was a lot. If you have any questions, go back, rewatch the parts you're confused about. And as always, please reach out. Thank you.